how can we show a representation of all points that make this thing equal to 7? Okay, well, so isn't that what happens when we create a graph of a curve or a line? We're representing a set of points, all the points that make something true. So let's graph that thing equal to 7. So x squared plus y cubed minus 2xy equals 7. Did anyone do that before we start, while you were doing the points? You thought of doing that? What's that? Then something's wrong. Yes, sir?
How come if you don't put equals 7, it goes 3D?
Because then it's setting equal to z, a third coordinate. So if we graph the equation x squared plus y cubed minus 2xy equals 7, that is a representation of what you were trying to do. You were trying to find all points that made that expression equal to 7. All points whose x and y coordinates made that expression equal to 7. So if we just literally tell the graphing calculator just graphs sets of points. It just graphs sets of points. So x squared plus y cubed minus 2xy equals 7 is a set of points. And if you put that in a command line, it's going to show you all the points. Okay? And so here's all of them. Someone said it's a llama. Yeah, maybe it's a llama. I don't know.
That's what I said.
All right. So again, just to reiterate, so when you put an equation like this into GC, it's going to display all the points whose coordinates make that equation true. And so that's what you were doing manually. You were trying to find all those points. But the equation is the same exact idea. It's going to show you all the points. But it takes too long to sit there and go dot, 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 dot. So we just draw a smooth curve through all the dots. And it represents all the separate points. Make sense? Okay, so here we go. The equation and the graph are mathematically the same because they both represent what? What do both the equation and the graph represent? A set, right. A set of ordered pairs. They both represent a set of ordered pairs. So what about that set of ordered pairs relative to the equation? What's the relationship of that set of ordered pairs to the equation? Which ordered pairs are they? All the ordered pairs that make the left side equal to 7. Okay? They make the equation true. And how does that set of ordered pairs then relate to the displayed graph? That's the easy one, right? Well, you're looking at all those points. When plotted in the plane are all the points from the curve that form the curve. Okay, does the set of ordered pairs represent y as a function of x? Does it represent y as a function of x? Yes or no? No, why not? Okay. So someone said the vertical line test. Okay, that doesn't explain why y is not a function of x. So why is y not a function of x? That doesn't violate a function. Yeah. That's what it is. Given there's at least one x. There's x's that have multiple y values associated with them. Okay? So it's not predictable. It's not reliable, right? So for a given x, there would be more than one y value. That violates our meaning for function. Okay, so no. Is it valid to talk about the rate of change of y with respect to x? First of all, is it valid to talk about the rate of change of y with respect to x, even though y is not a function of x? What do you think? Yes or no? So here, look at x equals 3 has at least 3 different y values associated with it, right? So what if we focus on this one right here? Is it valid to talk about the rate of change of y with respect to x right here? What's that? Is it valid to talk about y? Yep. What about here? Is it valid to talk about rate of change of y with respect to x in this local area? Okay, what about down here? Yeah. Okay, so even though there's multiple y's for the same x value, 3, if you look in the local area of a curve, you can still talk about the rate of change of y with respect to x. It's valid. Okay? So then what about a rate function? Can we talk about a rate function? If looking at individual moments along the curve, it's valid to get y as a function of x. What about a rate function? So what would if a rate function is possible, what would the input, or what would the independent variable be? Does it work to make just x the independent variable for a rate function? Doesn't work, right? Like, again, when we're at 3, x equals 3, or x equals 2, or x equals 4, there's going to be more than one rate associated with it. So we have to kind of change the way we set up the rate function. Any ideas how we can have an independent thing that's going to make a true rate function? What would be our independent entity? If not the x value, then what? So what makes, say at x equals 3, what makes that one unique from that one, unique from that one? Y. So instead of an x value being our independent, no, not y. Both. Someone said x, y. Both. You make the ordered pair like your independent variable. So there's only, for any given ordered pair on the graph, there's only one associated rate of change. Would you agree with that? But for any given x value, there could be more than one rate of change. So we change it and we make our... Okay, so we answered that before. So what we do is we say, yes, if the input is an ordered pair x, y, and not just a value x, then it makes sense to talk about a rate function. Because for any given ordered pair, there's only one possible rate of change at that point on the graph. Or at what we call a moment around that, okay? Okay, so in order to determine this rate of change of y with respect to x, what we have to do is we pretend that y is a function of x. So we said that y is not a function of x, but we pretend that it is. We pretend that it is. And so then, in other words, y as a function of x, y equals f of x is implied, okay? But does not necessarily exist. In fact, we're looking at this picture and we know it doesn't exist, right? Y is not a function of x. But we pretend it exists. In order to get this rate function, we say it's implied that y is a function of x. And so then what we do is what's called implicit differentiation. This idea that y is a function of x can only be implied even though it's not really true. It's not really true. So, and y is not, and looking at the equation, y is not a function of x because they're totally tangled up. Do you see this? It would be very difficult to solve y equals some expression of x's, okay? Because the y's and x's are all tangled together. Like, how do you get y out of that so that there's only x's on the right? You can't. And that's showing up in the fact that, for a given x, you get more than one y in some cases. All right, but we pretend. We say, okay, let's just pretend y is a function of x, and then we do what's called implicit differentiation. Okay, so here's how it works. We start with the equation. And so rather than having y on the left and all the x's on the right, so we're going to take the derivative term by term, right? So we're just going to take the derivative of each individual term as they're added and subtracted. But thinking of y as a function of x. So this is what it's like, x squared plus f of x cubed minus 2x times f of x equals 7. F of x, implied but not real. Okay, it's not factual. So we just consider that it does exist. We pretend that it exists. Okay. So then we do we're going to take the rate of change of both sides, the rate of change of the left and the rate of change of the right. And now we're going to use all our rules that we learned. So we get the rate of change of the sum or difference. How do we take care of that? Nothing easier than that, right? We just do the individual rates of change. And then over here on the right, what's the rate of change of 7? 0. Okay, it's going to be 0. It's going to be 0. We're going to have the rate of change 0 on the right, and we're going to do each one of these. When we get to f of x cubed, and we're taking the rate of change of f of x cubed, what will we have to use? We've got a function plugged into x cubed. So we need chain rule. And then we got 2x times f of x. What are we going to need? Product rule, right? Product rule. Here we go. Oh, no. Here's where the pen takes over. Okay, so we're going to do rate of change of each of these. Rate of change of x squared. That's easy. 2x. Okay, rate of change of f of x cubed. 3 chain rule. F of x squared times f prime of x. Chain rule, right? Chain rule. It's implied that y is a function of x. So if we have y cubed, it will require the chain rule. Okay, minus. Here we go. First times rate of change of the second. Okay, plus rate of change of the first. Let's see, how do I want to do this here? Just put parentheses around it. So first times the rate of change of the second, plus second times the rate of change of the first. And that all equals rate of change of 7. Okay, did you follow it? So what was our goal? Our goal was to find dy dx, or the rate of change of y with respect to x. Where do we see that in there? Where do we see that dy dx? Oh, come on. Alternate f prime, alternate notation, right? F prime of x is the same, just a different notation for the rate of change function, dy dx. So what we're going to do is we're going to get all the terms that have an f prime in them and keep them on the left. Any term that doesn't have an f prime is going to the right, because our goal is to solve for f prime. So again, any term that has an f prime, keep it on the left. Any term that doesn't have an f prime, send it to the right. So this one's going to stay. 3 f of x squared times f prime of x. Okay, what else is going to stay? This one here. It's going to be minus 2x f prime of x. That's my left side. What's on my right side? This is going to move over. So when it moves over, it becomes negative 2x. What else is going to move over? 2 times f of x. But notice it's minus, right? This minus goes into this. So it's going to move over. This will move over as plus. Did you catch it? This is on the left side. This is actually minus 2 f of x. So on the right, it would be plus. Good so far? So how am I going to solve for f prime? I've gathered all those on the left. All the ones that don't have an f prime are on the right. So I'm going to factor out f prime and then divide by what's remaining. After I factor out f prime, I just divide by that and I'll have it. So I'm going to give myself some room here. So, can I do 2 steps at once? imagine I'm factoring out f prime, factor out. What's going to be left when I do that? 3fx squared minus 2x. So to get f prime by itself, I'm going to divide by that. So I'll have minus 2x plus 2f of x, and that will all be over what I got after I factored out f prime. 3f of x squared minus 2x. Did you catch it? Factoring out f prime leaves me with this minus this. And I'm going to divide by that. Okay, but what was f of x in the first place? That was just y. That was just y. And what did we say our independent entity was going to be to find the rate of change? An x, y, and look at what it's become. This rate of change is a function of what? X and y, right? So combined. You need an ordered pair. You need the x and y value. And having the x and y value, you're going to, so this really is not just a function of x, but and y. So we can change our notation to dy dx. Because really this f prime is really a function of both x and y. Okay? So this is a little misleading, okay? But what did we find? We found that our rate of change is dependent on ordered pairs, x and y. So for a given ordered pair, you take the x and y value, you evaluate this ratio, and that'll be the rate of change at that point. So let's try it. So let's go back to any questions on solving for that rate of change formula for this particular curve. We'll do another one. Okay, well let's kind of analyze this one and see. So is that what we got? So now I've entered that in. I've called it R, and I've made it a function of two variables, which it is. It's a function of x and y. And the formula negative 2x plus y, or 3y squared minus 2x. So let's look at this point where at this top point where x equals 3. I guess that's the best I can do. I'm going to zoom in on that. And just like we've done in the past, we're going to zoom in until the graph looks linear. I can't get it to give me the actual coordinates here. There it is. Okay, so that's the ordered pair 3, 2.2618. So right now you have two ways to get this rate of change. You have two ways to get the rate of change in the vicinity of the point 3, 2.2618. What is one way to get this rate of change? What is one way to get this rate of change? You've got two ways, and we can do them both and confirm. What's one way? What's that? Put the numbers into? Yeah, so put the numbers into the equation. So I've defined that function, so I can just use GC to get me the value of R of 3, comma, 2.2618. I get negative 0.158, basically. Just doesn't want to, where is that? Close enough. All right. So how about that? Does it seem reasonable, that rate of change? Negative 0.158? Why does it seem reasonable or not? Yeah. Decreasing, so therefore negative, decreasing and negative, and then what about the value 0.15? Yeah, so for a change in x, are we seeing a large decrease in y or a small decrease in y? Like a 15% decrease in y for whatever change in x you had, right? So for whatever change in x you have, this is telling us that y is going to decrease like 15% as much, or 0.15 of that change in x. Does the graph look like it's showing that? Yeah. How can we confirm it? Grab 2 points. This is the other way. Now we've got a virtually linear part of the graph here, right around 3. We could grab 2 points and do what? Change in y over change in x, and we're going to get something really close to what that formula gives us. Okay? We're not going to do it just for time's sake, but find that change in y, change in x, find that change in y. Calculate dy over dx. Now that we're close enough in, so it's essentially linear, and that dy over dx will be very close to negative 0.15795. The equation is giving us an exact rate of change, right? Exact rate of change at the moment of that in the vicinity of that point. Okay. Does it make sense? All right, let's look at the other, just one more. So we said that there were lots of, at least 2 other places where x was 3. Let's just see how that works. Okay, here's another one. So if I come down to this point in the graph, okay, if we were to find dy dx manually, now that we have a virtually straight little piece here around 3, if we were to find that manually, what would you guess that the rate of change would be? Something like what? Positive or negative? Positive, and I don't know if my scales are exactly the same or not. But if my scales are the same, which I think they are they? Something like 1, right? Something maybe a little greater than 1. So here's the point, 3, and then what's the y value? Didn't write it down. Now I've lost it. Point, what is it? Can't read it. 0.34? Is that what that says? Look at that. Rate of change is 0.94, about 1, right? About 1. For a change in x, around 3. This point, 3 comma, what is this? 3 comma 0.34. The rate of change is, the change in y is pretty close to whatever small change in x that you pick, or a rate of change of 1. Okay, so see how this works? So the fact that you're plugging in an ordered pair, x and y, lets you differentiate between points that have the same x value. Any questions? So what was that? What was all the info on that first one? Let's look at this here. So at 3, we had the point 3 comma what? 2.2618, and our rate of change was? Who remembers how to graph a line? 15 what? Who remembers how to graph a line? Remember our what did we do for graphing a line? Y equals? No, we never did mx plus b. What did we do? We did old y plus change in y. And the change in y was calculated as m times change in x. Right? Old y plus the change in y. Change in y, m times the change in x. So we've got a point here, 2.2618, plus rate of change is negative 0.158. X is any starting point on a line, and A is 3. So what line would that be? I've got a point and a rate of change. What line would that be? If I graph this line, what will you see? It'll go through that point. And what else? Lots of lines go through that point. What else will you see? I'm about to plot this point. Oh, someone truly knows. Yeah, negative slope. Tangent line will be tangent to the curve. It'll have the same rate of change as the curve at that point, and it'll go through that point. So will it be tangent? Okay, so it's going through that point and it has the same rate of change at that point. So this is constructing the tangent line. If I zoom in enough, what will you see? In theory. I need to make sure I'm at 3, right? So I got off at 3 here. Yeah, I need to be at 3. There we go. Okay, that'll be better. So if I stay at 3 here, essentially we're going to see same thing, right? Because we know that if you zoom in close enough, our curve is essentially linear. Well, what line is that we're looking at? We're looking at that line, right? Going through that point with that rate of change. You see? And that's called the tangent line. Shoot, I wanted to do another one. Not enough time. Okay, so you'll watch a little video that'll go through another example of the implicit differentiation, like the one we did before, and then you'll have homework. We're going to do just Blackboard will have all the details, but we're going to switch to using a traditional textbook and an online homework system. Okay, but you will have written homework sometimes too. Just Blackboard will have all the details of how you get all that set up. Okay.